Yeah. So this Fibonacci sequence. Another sequence would be, for example, 0, 2, 4, 6, 8, 10, 12, on like that. Which is clearly just you keep adding 2. That's the pattern here. Yeah. Now, certain sequences come from very nice and easy rules, right? So I think pink's a good color for this. Can be defined by rules. For example, this one above, right, would be the sequence A with subscript I, with index I, so the ith element here equals 2 times I for all I greater than or equal to 0. Does that make sense? Like if you were to do this out, you get, okay, AI is 2I. Where do I start? Well, so for all I greater than or equal to 0. So I start with A0 equals, what does it equal? It's 2 times 0, which is 0. And then I have A1 is going to be what? 2 times the index, so 2 times 1, which is 2. A2 is going to be 2 times the index, which is 2 times 2, which equals 4. A3 is going to be 2 times the index, which equals 6. And you go on and on like this. So we get 0, 2, 4, 6, right? So this defines this sequence. And this is a way around the dot, dot, dots, in the sense that just say the sequence, so just say like this is another way to write that sequence, is this right here. It's the sequence of AI. It's the sequence where AI equals 2 times I for all I greater than or equal to 0. Does that make sense? So for example, let's say our rule is AI equals 2 to the I. Actually, better yet, AI equals I squared for all I greater than or equal to 3. What would that sequence be? Well, that sequence is, where do you start? Well, it's for all I greater than or equal to 3, so you start at 3. So you start at A3 is going to equal the index squared. So 3 squared, which equals 9. A4 is going to be the index squared, which is 16. A5 is going to be the index squared, which equals 25. A6 index squared, which equals 36. So our sequence here, our sequence is 9, 16, 25, 36, on like that. That's the sequence this rule describes. And as far as we're concerned in this class, every sequence has a rule associated with it. Although, if you take advanced calc, you'll find it's not exactly true. But yeah.
Could the rule be defined recursively, like for the Fibonacci?
Yes. Yes. We're going to get to that probably in next week's class. But I'll show you right now. The rule here, there's no real nice rule you can write down. In the sense, there's no rule you can write down where like AI is straight up equals some function of I. You can't do that with Fibonacci. You can say AI equals about, I think it's what, like phi to the I or something like that. But you know, but it's not gonna be exact. Where 5 is the golden ratio, it's really interesting. But what you can say is that you can define like A of 0 to be 1, A of 1 to be 1, and then A of I plus 1 to equal A of I. Actually, no, you want A of I plus 2. You want A of I plus 2 to equal A of I plus 1 plus A of I for all I greater than or equal to 2. And then notice you're fully covered, right? Like you know what 0 is. Actually, no, I'm sorry. I want for all I greater than or equal to 0. Or maybe it would make more sense. That's correct what I just wrote down. Maybe it would make more sense to say AI equals AI minus 1 plus AI minus 2 for all I greater than or equal to 2. Now it's clear we're covered because we know what A0 is, we know what A1 is, and then we know what AI is for all I greater than or equal to 2. So that means we know AI for everything. And there's only one thing to check here, and that is to make sure that these are even accessible, right? So we have to make sure that for all I greater than or equal to 2, AI minus 1 is defined, and AI minus 2 is defined. That's fine because when I equals 2, we have 1 and 0 already defined right here as like our conditions, like our initial conditions, basically. It's a whole thing. We'll get to that more later, but you're totally right, Alex. So maybe, yeah, so I think this makes sense. So we can use rules to define sequences, but also we can take a sequence that we know of and make a rule for it. So let's try that real quick in the last couple minutes of class, and then we'll all go home and have a good weekend. So, or a good Friday, whatever you guys do. So, let's have an example. So I'll say find the rule for the following sequences. And so note, a rule has a function f such that AI equals f of I and some lower bound m such that AI equals f of I for all I greater than or equal to m, right? That just tells you your starting place, and that tells you how to calculate AI based on I. Don't get too caught up in the function thing. I'm just saying that f of I here just depends on I, and you get there's some rule you can get to AI. So, for example, what if you had 2, 4, 8, 16, 32, 64, baby example, but we're starting off. What would that rule be? Oh, what do we got? We got the chat's blowing up. 2 to the I. All right. So we have AI equals 2 to the I. But where do we start? Like if I looked at this rule, I go, okay, do I start with A0? Yeah. For all, yes. So for all I, you could say greater than 0. I'm going to say greater than or equal to 1. Yeah. Totally right. And this totally defines it, right? If you recreate this, you see you'll get 2, 4, 8, 16, 32, and 64. Is this the only possible rule you're going to make for this? Benet says no. Why is it no, Benet? So they're typing or thinking.
It's like 2 times AI minus 1 or something. That also works.
2 times AI minus 1. Oh, you could write it recursively, yeah. But if we're not writing it recursively, if we're writing it in this way, where AI like is a function depending only on I, not on any previous AIs, but only on I. Yeah. Alex brought up a good point. What if we say AI instead equals 2 to the I plus 1 for all I greater than or equal to 0? Now our I starts at 0, but everywhere we're plugging in an I plus 1. So we think about this, right? Here, we start at 0. A0 is going to be 2 to the 0 plus 1, which is 2 to the 1, which equals 2. A1 is going to be 2 to the 1 plus 1, which is 2 squared, which equals 4. A2 equals 2 to the what? To the 2 plus 1, which equals 2 cubed, which equals 8. Right, 2, 4, 8. That's the sequence, right? So all we did here basically is we took this AI equals 2 to the I for all I greater than or equal to 1, and we kind of just shifted the indices. Right? Instead of starting at 1, we start at 0, but then we have to kind of correct that here and then add 1. So we shifted the indices left, but then we had to shift what we plugged in right to kind of make it work out, if that makes any sense. But I mean, there's infinite ways to do this. You could have AI equals 2 to the I plus 2 for all I greater than or equal to -1. You could have AI equals 2 to the I minus 1 for all I greater than or equal to 2. And you could, and these are all separate, by the way. These all, like, all these I's are different. Don't get them confused with each other. These are all separate things. But there are different ways you can write this one sequence. Does that make sense? None of these are more right or wrong than the other. The point is just know there's a few ways that we can think about this. And there's also to do with what I was saying before, where you start is kind of arbitrary. Like you call this A2, A3, A4, A5, A6, A7, on and on. If you decide to start at 2, you have to use this rule. Where should you start? Doesn't matter to me. Pick the one that's easiest for you. Now, real quick, before we leave, what's the rule for this? Sequence 5, 9, 13, 17, 21, 25.
Four I plus 1.
For all I greater than or equal to.
Greater than 0 or greater than 1, greater than or equal to 1. Yeah.
Perfect. Like it a lot, right? Because all these just add 4 between them, right? And where you start kind of, well, so here's what's interesting, right? This totally works, right? If you plug it in, you go, okay, well, 4, you start at 1. 4 times 1 plus 1 is 5. 4 times 2 plus 1 is 8 plus 1 is 9. 4 times 3 is 12 plus 1 is 13. That works, right? It might be easier to think about it this way. It's always going to be 5, and then we have multiples of 4 here. We're adding 4. So it'd be easier to think about it as 5, 4 times I. This is for all I greater than or equal to 0. Again, it doesn't matter. The same sequence, just where you start's different. But anyway, that's a good first start to sequences. But we'll do the rest next week. Sorry for keeping you late. Any questions, anybody? Cool. Well, have a great weekend. I hope You're a little disappointed to leave contradiction and contrapositive proofs because they were kind of cool, but can maybe breathe a sigh of relief that we're doing something a little easier for a second. In a couple days, it's going to ramp up. But for now, take a well-deserved sigh and relax and be happy. Thank you, Benay.
Of course. Thank you.
That sigh sounded well-deserved. Yeah. But anyway, have a great weekend, guys.